Welcome to Chem 230 with Dr. Bob Blake at Glendale Community College, and we have been talking about the electron configuration of carbon. We looked at carbon in its ground state and then carbon in excited or forbidden states so that you get a little bit of an understanding of the different rules and guidelines for writing electron configurations. And you can write ground state electron configurations for any atom in the periodic table. There are plenty of exceptions, so if you're taking a more advanced class, you may need to look at the exceptions and which atoms have exceptional or non-predictable electron configurations. But the basic tool that's really important to understand, I like to diagram out, and that's the orbital filling order. So the lowest energy level is the first energy level. And if you're going to put electrons in the first energy level, there's only the 1s sublevel, and it only has room for 2 electrons. So that's your starting point for writing electron configurations. The second energy level has 2 sublevels, which are at slightly different energies. And this diagram is not going to be to scale. In actuality, the second energy level is much, much higher than the first energy level on this relative scale. But just so we can fit everything in, I'm going to be drawing things with the wrong spacing but the correct order. So the first energy level only has room for 2 electrons. There's a single orbital with its room for 2 electrons. The second energy level has 4 orbitals, the 2s and 3 2p orbitals, and so that provides room for 8 electrons in the second energy level. So as you're filling electrons into the electron energy diagram or writing the electron configuration, you put the first 2 electrons in the 1s sublevel, the next 2 electrons go in the 2s sublevel, and then there's room for 6 electrons in the 2p sublevel. And so after you've filled the second energy level, you go to the third energy level, which has 3 sublevels, the 3s, the 3p, and the 3d. And so you would expect to fill those in that order: 2 electrons in the s, 6 electrons in the p, and then 10 electrons in the d. But it's sort of interesting because the 4s sublevel is slightly lower in energy than the 3d sublevel. So for neutral atoms, your filling order is not that you'd complete the third energy level before moving on to the fourth, but you fill the energies in this order: 1s, then 2s, then 2p, then 3s, then 3p, and then the 4s sneaks there in between the 3p and the 3d. And so then after you fill the 4s, then you can go to the 3d and fill that one. And then you continue on with more of the fourth energy level, so you do the 4p. And if you wanted to know the complete ordering, you could actually use the periodic table as a map to get these orbital energies in this order. And that has to do with where the outermost electrons are and how that affects their chemical properties and thus where they sit in the periodic table. But after we finished the 3d sublevel, then we'd move into the 4p and be able to fill those. And then after the 4p, you might expect to go again and fill more of the n equals 4 or fourth energy level electrons, but again the 5s is lower in energy than the 4d. So you'd fill the 5s and then you'd fill the 4d. And so this energy ordering almost has to be memorized, unless you can use the periodic table as a tool for that. And in this course, carrying through to the 5p, And then the 6s would be as far as we're really going to go. And this would account for up to 56 electrons. So if you counted all the electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56 electrons. So if you have an atom with 56 electrons or less, you would only need to go up to the 6s sublevel to write its electron configuration. So if I just picked any old element on the periodic table, such as silicon, the neutral silicon atom, and actually let's go a little higher, let's go up to selenium, so we can see a bit of the funky ordering. But if we went to go to selenium, we look on the periodic table and we see that selenium, if it's neutral, has 34 electrons. And so if we wanted to write the electron configuration, we'd start at the bottom with the 1s, put 2 electrons in there. Then we go to the 2s, put 2 electrons in there. 2p gets 6 electrons. And then 3s gets 2 electrons. 3p gets 6 electrons, and this is where we might expect to go to 3d, but no. After putting the 6 electrons in the 3p, we go to the 4s and put 2 electrons in there. So now I've filled 10, 20 electrons. We have to go 34, so we keep going. And we can put 10 electrons in the 3d. So that's 30 electrons. We have to get to 34, so we have 4 remaining to put in the 4p. And notice when I'm filling, I started following Aufbau. I start in the lowest energy orbitals, and I fill higher and higher in energy until I get to enough electrons. But then when I get to the 4p, I'm going to put 1 electron in each orbital before I start pairing. So the 3d gets 10 electrons, the 4p gets 4. So there's our electron configuration for selenium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. And you can see it in the diagram that there's 2 unpaired electrons and which orbitals have which electrons in them. And as before, I followed the Pauli exclusion principle that if I have 2 electrons in the same orbital, I have to give them opposite spins. So this ordering is something you should be familiar with. I've got it written out in a line as per electron configurations, and then I've got it in the diagram, which I like a little better because it shows where the unpaired electrons are, which is important to know for chemical properties and magnetic properties. So next video, we'll try to explain how you can get this ordering and see that the 4s fills before the 3d from the location of the elements in the periodic table.